that. You'll have to probably say got it on there, got it here. And we will start the recording to the Zoom. You're going to have to say got it again. Maybe. No, we're good to go. Admits. I'll take care of the admissions. All right. Hello, everyone on YouTube. Hello, everyone in the room. It's great to have you here. Let me make sure we are Zooming. Yes, we are tubing. Yeah, we're tubing. All right. Well, it is my pleasure today to introduce our speaker for the Water, Wetlands, and Watersheds seminar. This is a close. And today we have with us Charmaine Siddiqui. So Char is 3 weeks away from defending her dissertation. So we have two options. We can either be very brutal with her, so that like the bar is so horribly low that her defense will be like a cakewalk, or we can be kind, or maybe we'll probably be kind. So Char started working in my lab in 2018. It's an interesting story. I was involved in a multidisciplinary cohort of folks studying the Amazon, and we were running and participating in a seminar. And Char was in the seminar, and I thought, well, who's this excellent graduate student? She seems so aware. She's like the most kind of like up to speed of any of the students, and who's a professor. And then I realized she was an undergraduate student, and I was very lucky to be able to recruit her to work in the lab. That was 2018. Char's getting ready to defend. She already has one of her, she has her undergraduate from agricultural and biological engineering here at UF. She has the first dissertation chapter published, the other one sort of along the way, but also a couple of other papers from side projects that Char's been working on. Char is nothing if not curious, and that curiosity has led you to a lot of tangents that have been very fruitful and interesting, including some work with a group down in South America called Rios Vivos Andinos. And she's made a lot of collaborators, both within UF and outside, with my guidance, without my guidance. Char is incredibly smart and hardworking and incredibly kind. I think the lab would probably put one of her highest qualities as being generous and being curious and unsinkable. So if the data, time after time, there's an issue with the data or there's a problem, Char is unsinkable in all things. So with that, Charmaine Siddiqui.
Thank you, David. Thank you, everyone, for being here today. So as David said, in 3 weeks, I'll be defending my dissertation. I wanted to start off my presentation with just a little overview of my dissertation and where this fits into context, and then a detailed overview of this chapter, fire disturbance impacts on Amazonian floodplain forests.
So just click one more time on the screen, because use the mouse to click on the screen, and then you should be good. Yep.
There we go. Right, so my dissertation is titled Quantifying the Effects of Landscape Disturbance on Ecosystem Response and Resilience in the Amazon Basin. So to set the stage for this area, the Amazon Basin is the largest watershed in the world, one of the largest intact forests, and is home to, produces 15% of global discharge, with the Amazon Basin outlined in blue here, and is home to 10 to 15% of terrestrial biodiversity within the Amazon biome itself. It is globally important for that reason in the regulation of atmospheric, hydrological, and biotic interactions. And simultaneously, it is facing unprecedented disturbances in the forms of deforestation, fire, climate change, and dams. And that raises questions for many researchers from many different fields of how are those disturbances going to affect the functioning of this basin as a whole. So for my dissertation, I had 3 major research aims that were distinct but connected to each other through this framework. So in chapter 1, aim 1, I was focused on the flow regime. A regime is a way to characterize spatial and temporal variation in a system property, in this case, stream flow. So I was looking at the flow characteristics of Amazon rivers across 5 different countries to characterize them in ways that were useful to ecologists, resource managers, and to set the stage for how those natural flow regimes might be affected by those watershed stressors, such as land cover change and dams. In my second aim, I was interested in characterizing aspects of the fire regime in an area of the Amazon that was facing one of the highest levels of fire and deforestation, and seeing how components of that fire regime affect the flow regime in that same area. And then in my third chapter, which I'll be talking about today, I was interested in looking at forest resilience and stability in a system of the Amazon that is highly influenced by the flow and the flood pulse, and how that system would be affected by components of the fire regime. So to talk a little bit about Amazon floodplain forest, this area spans 250,000 square kilometers and is highly influenced by the Andean mountain region. It is inundated, can be inundated for up to 10 months of the year. And during that time, it can experience up to 15 meters or 50 feet of variation in water levels. Here's a picture here from one of our collaborators of what that variation in water levels can look like during the dry season, low water period, and up to the wet season. Floodplain forest species have thus co-evolved with this dramatic flood pulse to be able to develop certain adaptations and really exist in tune with the flood pulse. At the same time, floodplain forests may be vulnerable to fire disturbance. So for the Amazon basin as a whole, there's been reports from 2019 onwards of much higher than expected fire activity happening. And this trend has continued in the previous few years. 2022, for instance, had the highest fire season in over a decade. And this loss of forest has cascading implications for the Amazon, but also for the floodplain forest of the Amazon, for fish that are reliant on those floodplain forest species, the ecological dynamics that exist between trees and animals there, humans that are connected to the system itself, and the climate as well, because in many portions of the Amazon, forest climate interactions are highly connected and tuned into each other. So with a certain amount of forest loss, you would also expect a change in the precipitation regime. So in floodplain specifically, there's been some studies that have come out to show that floodplain forests may be even more vulnerable than uplands when it comes to wildfire disturbance. This can be attributed to the ways that floodplain forests differ from those upland forest species. For example, they've developed, so one example is that they tend to accumulate a lot of fuel in their topsoil, and during fire events, that fuel provides a greater source of burning. They also have specialized adaptations that are great for flooding periods. One of those is root mats, which are intended to cover a lot of that fuel in the topsoil. However, those root mats are also highly flammable. So if a fire occurs in that area, it can be either a low-grade fire, but still one that has an effect on forest health over time. And then another recent study found that after one fire event, floodplain forests can come back and recover their original ecosystem dynamics, but after a second fire event, that's much less likely to happen. This image right here is an example of what one of those fires might look like in Rio Branco, the capital of Acre. This comes from a report from the Washington Post about how these fires in floodplain forests are affecting both the ecology and the human settlements that live there. And in this case, one of the effects for humans is that because of these fires, there is changes in the precipitation regime, where it was easy before to rely on the floodplain forest for agriculture, water, and food. That is no longer as much of an expectation. And so then moving from field studies to what can be seen from remote sensing and on a larger scale, on this graph right here, we have remote sensing and tree cover distribution data. And on the x-axis, we have time after a fire. On the y-axis, tree cover distribution between floodplains and upland forests. And after a fire, it seems that the floodplain forests tend to have a greater magnitude of change in their tree cover distribution. And compared to the upland forests, it does not really seem to recover. And for that reason, they do seem to have stronger and longer lasting impacts on their forest structure compared to the uplands across the entire Amazon, and have been termed the Achilles heel of Amazon forest resilience, because it is conjectured that if they do experience that wide scale level of fire disturbance, that they would not be able to recover as quickly. And so beyond that, one aspect of the floodplain forest that has not been looked at as closely is the forest diversity that exists within those floodplains themselves. So within this system, there are 3 types of floodplain forests: blackwater, clearwater, and whitewater, that all have their distinct ecologies and levels of productivity. And yet our knowledge regarding fire disturbance and in floodplain forest and vegetation is biased towards blackwater Idaho forests, which only account for 15% of Amazonian floodplains. The majority of them is actually this whitewater floodplain which in this map here, the tributaries which are dominated by whitewater, blackwater, and clearwater forests are shown in tan, black, and blue respectively. So there is this raises the questions of when you have these different types of ecosystems in this area, would they have different fire regimes to begin with? And how would those different forests respond to fire disturbance? And to speak a little bit about the variation in these different types of floodplain forests. So in our study area, we have blackwater and clearwater, nutrient poor EGAPO forests, that's usually what they're called, and nutrient-rich Varzea forests, whitewater forests. This exists along the spectrum from low productivity, intermediate, and high productivity, low pH to high pH, and low species richness to very high species richness. And so this then sets the stage for determining if these ecosystems are so different in their ecosystem and molecular properties, how might those have different stability, have a different level of forest stability after a fire disturbance. And so then to introduce the concept of ecosystem stability, that would be how a system responds to external perturbations or disturbances. It can be characterized by resistance, variance, and resilience. So resistance is the ability to withstand a perturbation. For instance, in this graph right here, if you had something that moved just a little bit versus a lot, the system that moved just a little bit would have lower resistance, would be able to respond with less change after a disturbance. Variance being a measure of spread and what the variation looked like before and after a disturbance. And then resilience is defined as the rate of return to a previous state. And from a stability standpoint, we'd be interested in whether that system responded very quickly and had high resilience, or if it responded more sluggishly and slowly and it wasn't as quick to recover. So those three things together can give us a pretty good idea of how stable a system is from a remote sensing standpoint. And so my question here is, where and how do forests differ in ecosystem stability in response to a fire disturbance? And so of all of the forest pixels in my analysis, they can be categorized into undisturbed completely, like they didn't really have a major disturbance, disturbed and then recovered, and then disturbed and did not recover. And for simplicity and for this presentation, I'm going to be focusing on the recovered forests, so those that experienced a disturbance and then were able to recover. And I'll talk a little bit about how we decided what was recovered. And then thinking about how those recovered forests might differ between whitewater forests and blackwater forests. And then a second factor of how this might differ along a floodplain gradient from the highest upland forests that aren't that relatively affected by the flood pulse, to floodplains in the middle, to seasonally floodplain forests, which during the wet season, their canopies are completely inundated. During the dry season, they are exposed. Oh yeah. And so to just review my objectives and hypotheses for this chapter, the first part is mapping the fire regimes themselves. So one objective here is to quantify fire regime magnitude, frequency, and trend. And I am hypothesizing that fire regime characteristics will vary by ecosystem type in the blackwater, clearwater, and whitewater. And then for my ecosystem stability metrics, I am hypothesizing, I'm first interested in wondering if there's differences between blackwater and whitewater to begin with, but I'm hypothesizing that when it comes to magnitude, variance, and resilience, that whitewater forests will be less stable compared to the blackwater forests. And the reason behind that hypothesis is that because those whitewater forests are so productive and the ecology of them is tied to those flood pulse dynamics and a natural or lack of a fire regime in general, there is some reason to believe that they might respond more strongly. And so to just touch on to my methods and data collection, all of the data was collected and processed within Google Earth Engine and then later processed more in R. I used, for mapping the fire regimes, I used the Modus Burn Area product from 2001 to 2022. And for determining the levels of disturbance that happen in forests and assessing their recovery, I used Land Trender, which is a series of algorithms in Google Earth Engine developed by scientists at Google for the purpose of monitoring forest disturbance. I used an algorithm within that program called Change Mapper to select my case studies to begin with. So I chose about 15 whitewater case studies and 12 blackwater case studies. And for each of those, I downloaded annual vegetation indices from 1985 to 2022. So an almost 40-year period of record. This is an example of what some of those time series might look like in this example in Washington State. So for a particular study area, you have all of these slices of data, and you can, and using a particular vegetation index, we can see how that metric of vegetation health, in this case, might have changed over time, when it could have been the most disturbed, and what that recovery trajectory might look like. That's what I did there. To be able to group the pixels that I had downloaded with respect to the questions that I'm interested in, I used this ecosystem typology map from Rios via Mazar to group my forests into blackwater, clearwater, and whitewater, and to think about what was the most seasonally inundated floodplains versus uplands. I used a wetland mask from Hess et al., which used SAR, synthetic aperture radar data, to provide a land cover classification. And then to speak a little bit on the vegetation indices that I used normalized burn ratio and normalized difference vegetation index. So NBR is a measure of burn severity. It's the normalized difference of near infrared and shortwave infrared bands shown here in the left image. And then the NDVI is used to quantify vegetation greenness and is useful in assessing changes in plant health. It's the normalized difference of near infrared and red bands. So while both of these bands contain the near infrared band, one of them is used to specifically think about burn severities and how severe a burn was using shortwave infrared, which connects to temperature. And then NDVI is really about plant health and could be incorporating other disturbances such as clear cutting, such as biological pest invasion. It incorporates all kinds of disturbances. And so tying those together to think about when a forest was disturbed using NBR and how I tracked its recovery. This is a conceptual or an example of what that process looked like. So based on previous literature in Amazon floodplains, Barbosa Castillo said that at 30% of a decline in NBR, we saw much more significant changes in forest structure. So that's the threshold that I used to define when something was disturbed, shown here in red for this time series. And so when a disturbance was noted, we went down to the same period in the NDVI time series and marked that as a potential disturbance. Then we used a pre-fire interval of 5 years to determine what were the mean and one standard deviation of pre-fire conditions, and when and if the forest time series got back to that period for another 5 years, was that forest deemed as disturbed and then recovered. So that's kind of the framework that's used here to assign all of our pixels to whether they were recovered or not. And now to talk a little bit about fire regimes and how those were computed. So they were computed for about 103 basins in 2001, 2020. I calculated magnitude, frequency, and trend. So magnitude was defined as the proportion of burned floodplain forests divided by total floodplain forest for each of my tributaries. I calculated cumulative burn area and peak burn area. And in addition to proportion, I also will be showing the total amount of burned forests. Frequency, in this case, is defined as return interval of a fire event. So I defined it as the period of record divided by the average number of times a pixel burned. And then the trend was defined as a Mann-Kendall test of the annual burn proportion of each of those time series to see whether it was increasing or decreasing. And this is just an example of what that might look like from my Google Earth Engine computer as I was working. So we had our forests here, floodplain forests in green, and MODIS burn pixels at a higher resolution in red, or lower resolution. And then for the stability metrics, I have calculated 2 for resistance, 1 for variance, and 3 for resilience. So resistance was defined in 2 different ways. One, the greatest decline in NBR, so it's most negative change for a time series. The effect of changes in NBR on changes in NDVI. For variance, I calculated the coefficient of variance, so standard deviation over the mean. And then for resilience, I found 3 different ways to look at it. One was when a time series was disturbed, how quickly, how many years did it take for it to recover to that to match that pre-fire disturbance interval, and then two different ways of using autocorrelation. So autocorrelation is a way that has been used to measure resilience in the past. One of the ways of doing it is seeing how similar a time series is when it is recovering. So a time series that recovers more quickly would be less autocorrelated than one that took more slowly to recover. And in that way, it reflects the sluggishness of that recovery, the bounce back. And so I'm looking at that. I'm looking at all of these metrics in recovered time series, and we're interested in seeing through this autocorrelation metric, how quickly was that bounce back. And then another metric of autocorrelation that has been used in the past is the change over time. That relates to this phenomenon called critical slowing down, which posits that if you have a system that is about to go under a state change, right before that state change, it might be much more self-similar to over time. And so I was interested in seeing if through my case studies, we were also able to see that. So to now jump into my results, starting with mapping of fire regimes. For the study area, I found that 1,830 square kilometers of floodplain forest have been burned from 2001 to 2020, and that annual cumulative burn area was higher in the Clearwater floodplain forest. The average annual cumulative burn area was about 29 for Clearwater, 24 for Whitewater, and 23 for Blackwater ecosystems. And then when we think about the average peak burn, so the average of all of these peaks of the year, it was 17 for Clearwater, 16 for Whitewater, and 14 for Blackwater. And just to make sure that I've reviewed what this graph is showing. So this is for Blackwater, Clearwater, and Whitewater, all of our tributaries, and the sum of their cumulative burn area over time shown here at the monthly scale. Cumulative burn area then sums everything up that happened within a year. So, oh yeah, and so then these are particularly 3 years that had the highest burn events that happened twice in Whitewater tributaries in 2015 and 2001, and also in Blackwater tributaries 2001. All of these had between 50 to 60 square kilometers of burn in that across all of their tributaries. These were periods that had high levels of drought across the Amazon. And I noticed that in the 2005 and 2010 drought, there was not much correspondence between the Amazon level droughts that occurred and the specific floodplain area. However, that is much more seen in 2015, where those floodplain forests did appear to experience higher than average burn events. And also to add some context here, I wasn't able to find an exact comparison, but we found that in the 1970s period to 2008, about 3,600 square kilometers, so almost double this amount was burned. And this indicates that previously it appears that more floodplain forest was lost in that late 1900s period. In this time period, seems like that has been less so. And so just to put it in context for this specific time period, seems that there was less than in the past. And so now to look at that same map time series as before, but scaled by the floodplain area itself, that does change the interpretation of this graph. So now instead of the highest events happening in the Whitewater and Blackwater, the scale changes much more when you scale it by area. So now the highest burn areas as a proportion occur in the Clearwater tributaries, especially in 2004, then followed by the Blackwater tributaries and Whitewater tributaries last. And as a proportion of total floodplain area, this is about 1.43% of the total floodplain forest area being burned, which is not so surprising given that this is an area that should not really be experiencing burns in the first place. And it does add some further context to what we're seeing with those fires that we did observe. And yes, and then one of the reasons for this stark decrease in relative proportion is because the study area itself is much more dominated by Whitewater forests to begin with. Yeah. And so now looking at our fire regime metrics from a spatial standpoint, I saw that burn magnitude was highly localized towards northeastern Amazon floodplains. So a lot of extremely high fire activity happening in the Northeast. As a whole, it ranged from virtually 0 to 15%. And when we think about median burn areas with respect to each of these different floodplain units, there was a range of 2.87 square kilometers burned as a median in whitewater tributaries to 1.25 in clearwater tributaries. And then using an ANOVA, I found that there were not significant differences between clear, black, and white ecosystems when it comes to burn magnitude. Now moving on to median fire frequency. On average, forests that burned an average of every 19 years. So the frequency ranged from every 4.5 years to only having been burned once in this 20-year time period. It was highest in this same basin here that experienced the high level of burn magnitude, the Rio Paru do Oeste, and this one Blackwater tributary right here, the Kolari River. And the median frequency ranged from 16.7 to 19.3. Again, here we found that there was not significant differences between clear, black, and white ecosystems when we consider all of the floodplain tributaries at this scale. And then now going on to trend. So overall, main point of this part of the result was that there was little evidence to support increasing burn activity in floodplain forests. This map shows the places where burn activity or burn area decreased in blue and increased in more red shades. If only 3% of watersheds had significant changes, there were 2 increasing, one in the Solimoes River, portion of the Solimoes River, and one portion of the Madeira River, and a decreasing trend over here in the Trombetas. And in this analysis, I actually did find a significant difference between the whitewater basins and clear and black. So in that one, we found that trends were not significant, but they were different between the ecosystems. Okay, so that is the fire regimes portion. Now moving into the magnitude response to fire disturbance. So this graph right here, just to walk through it, here is upland forest, floodplain forest, and seasonally flooded floodplain forest, and a comparison of blackwater versus whitewater tributaries that I will show for each metric. And I've included a star here if there's a difference, a significant difference between the blackwater and whitewater ecosystems. And so for this first metric of resistance as defined by magnitude decrease in normalized burn ratio, we found mixed responses in this metric. So for floodplains, whitewater ecosystems had larger decreases in NBR. They were distinct from the blackwater and lower there. And in seasonally inundated floodplains, blackwater forest had larger decreases, but the disparity between their medians was much less dramatic. In uplands, we also saw that the greater decreases took place in floodplains. So a little bit of a mixed pattern here, but there's partial evidence that there's less change and greater resistance in those blackwater ecosystems. In the next way of looking at resistance, the hypothesis here is that when looking at change in NBR and change in NDVI, that you would have a generally positive slope and a positive correlation between changes in NBR, or your increasing fire, and your changes in NDVI, or your forest greenness and health. And I add on a hypothesis to that will vary by your ecosystem type. So it might be more dramatic of a response in thank you, floodplain forests, especially the seasonally flooded floodplain forests, and more so in whitewater ecosystems shown in the white, gold, and red, relative to their blackwater counterparts shown in black, gray, and blue. And so, yeah, that is the hypothesis. Then looking to our actual results that I saw, I found that seasonally flooded blackwater forests had the highest slopes and that they were significantly different than all other ecosystem categories. So the general hypothesis of there being a positive correlation between these two variables was found, and that in seasonally flooded ecosystems, especially blackwater, it was even more positive and significantly different from the rest. Now, when looking at the scatter of that data, so these are the regression lines that were derived from these data. I found it really interesting that when we saw the scatter of the actual points, that there's two different trends going on here. There's sometimes where there's a positive correlation between NBR and NDVI, but then there's other times where that relationship is even more pronounced and an even more sensitive slope. And so that split response could be attributed to changes in land cover. It's possible that the wetland mass that I'm using to classify whether something was a floodplain forest or not, it could have changed over time in a way that was detected by the Landsat data. It's also possible that previous fire history might explain this difference in sensitivity. So previous studies have said that floodplain forests respond differently after one fire versus two fires. And I wonder if that different pattern that we're seeing could be explained for that. That would be an opportunity for future research. This hypothesis partially supports that there's greater sensitivity in floodplain forests. And instead here we see a greater sensitivity in black water compared to the white water. Now moving on to variance. So variance was highest in whitewater ecosystems, consistently in uplands, floodplains, and seasonally flooded floodplains. It was higher across the board. And this analysis suggests that there is relatively decreased stability in those whitewater ecosystems. So that's variance. And then for resilience, the three different metrics that I was looking at, we'll go through those now. So first one is recovery rate. So blackwater forests recovered more quickly than whitewater forests. The average recovery time for all recovering forests was 4.4 years. And every year that they recovered, it was by about 0.2 units in NDVI. In the floodplain forests and seasonally flooded floodplain forests, the whitewater forests took longer to recover. In upland forests, this response was switched, indicating that it does matter what type of forest you're looking at when making this, making those inferences about floodplain stability. And so this supports the hypothesis of higher resilience in blackwater floodplain forests. Now going on to autocorrelation, that metric of sluggishness and how quickly or slowly a forest bounced back. So autocorrelation ranged from -0.5 to about 0.75, was significantly different when looking at upland, floodplain, and seasonally flooded differences in the black and white forests. And I saw that whitewater ecosystems and seasonally flooded floodplains especially had higher autocorrelation coefficients across the board. And so this metric supports the hypothesis of higher resilience in the blackwater floodplain forest, indicating that those would be more quick to recover. And then for trends in autocorrelation, I saw pretty mixed responses in this graph. So in uplands and seasonally flooded floodplains, the AR1 coefficient was increasing in the blackwater ecosystems. The trends were different between in seasonally flooded floodplain forests between black and white, but not really for the other two categories. And to just put this more in perspective, so since this is a Kendall-Tau indicator of trend, here's the 0 line. Things above that line were increasing, things below were decreasing. And from a previous study that was done on the entire Amazon scale, they found that the average trend in autocorrelation was between 0.3 and 0.4. And at that scale of analysis, they were suggesting that the Amazon basin was getting close to that critical slowing down period. I did not really see that with these case studies over this time period. So it did not conform with those previous results. And so this provides limited support for the higher resilience in blackwater floodplain forests. It was a little bit more mixed for this metric. And so the main findings overall are for the mapping of fire regimes, we found, I needed to update that. Next one, we found that only trend was significantly different for each other. And we were able to map those fire regimes in terms of magnitude, frequency, and trend. For magnitude response to disturbance, I saw that fires caused greater declines in forest health in seasonally flooded forests with the greatest sensitivity in blackwater forests. And when looking at that metric of resistance, that whitewater floodplain forests experienced greater burn severities. For variance, that one very clearly aligned with the hypothesis. It was across the board higher in whitewater ecosystems, and it was significantly higher in the seasonally flooded forests compared to other types of forests. And then for resilience, we saw a few mixed results. For recovery rate, the blackwater forest recovered much more quickly, and autocorrelation was lower in those systems. When thinking about trends over time, it was a little bit more mixed there. So the overall take home from this set of results is that the stability metrics that I looked at here confirmed that floodplain forests were more vulnerable to fire disturbance compared to uplands, and the variance in resilience metrics providing evidence for lower stability in whitewater floodplain forests. Some future directions for research include determining what features may cause differences in sensitivity of fires to forest health. So determining why we had that split regression pattern in the scatter plot of between fire and forest health, to look at the impact of compound disturbances. So this area we know is already sensitive to changes in the flood regime, changes to fire. What about when those two things are paired together? This is a very unique and complex system to be able to ask those questions and keep looking at the levels of complexity that exist. And lastly, this remote sensing scale analysis really promotes and confirms the need for field monitoring of disturbance in those floodplain ecosystems in both blackwater and whitewater floodplain forests, with a focus on the species level response to disturbance and how that would affect the ecosystem dynamics. And so with that is my presentation. I thank you all for your attention, and I'll accept any questions now.
All right, excellent. Thanks, Shar. So we'll go to the room first, then I see some questions from YouTube already popping up. So let's start in the room.
Yes.
I just have a small question as to what do you mean by fuel in the topsoil? What is that fuel you're referring to?
So the question for YouTube, the question is what does Shar mean about fuel in the topsoil?
Yes, so that refers to the available biomass and the amount of like organic matter that is in that soil, especially the top layer, that is able, like burnable material.
Oh,
Mhm.
thanks.
Yes.
I was curious if you saw different variances in the length of the dry season between the different forest types. And how that kind of affected some of the.
That's a good question. So for my analysis, I picked an area that included, or a temporal period that included the most dry period. So from October to March. So I looked at the same time periods in those whitewater versus blackwater forests for the driest portion. For the more wet periods, it's actually a little bit more difficult to get clear and accurate remote sensing data. In the Amazon, there's so much cloud cover that it often distorts or prevents our ability to see what's happening. It's still possible though. So it would be interesting to see what happens with the available data that you would get.
So there's a question from Amin Fidan on YouTube. She asks, well, she says, amazing work. My question is, what kind of ground truthing was done when quantifying fire disturbance, if any?
Oh, yeah. So with this analysis, it was done from a remote sensing scale. We used previous studies to kind of inform these hypotheses of how they might be reacting, but no ground truthing was done for this analysis. If it were to be done, I would think to be able to see what's happening as you have a forest recovering, it would be very important to see if it's recovering in a way that confirms it going back to the original forest distribution that you saw before the fire, or if it was recovering to a very different landscape.
So you showed us just the disturbed and recovered pixels. I know you're still working on chapter 3 as we speak, but did you see places or time periods when you had disturbance and no recovery?
Yes, yeah.
Yeah. Any like overarching conclusions about where that's occurring, or what that transition is going toward?
Yeah, so I would say the most of the data fell into the control pool of not being disturbed. After that, the biggest portion of data was pixels that were disturbed and didn't recover. The smallest was the portion that were disturbed and recovered. And for the differences in the disturbed never recovered systems, there are differences between Blackwater and Clearwater, Blackwater and Whitewater and along the seasonal gradient. I didn't remember exactly which ways that they do differ, but there are differences. It is an important part of the picture to be able to like add that nuance.
Could you well, maybe it'll be for your dissertation, but like, is it more likely to have it disturbed and non-recovered
Mhm.
whitewater
Whitewater.
system, because you're finding this slowness and sluggishness and increased time to recovery. So
Mhm.
you might expect that if it's less resilient, less resistant, then it would also be more likely to fall into that bin of unrecovered.
Right, that's a good point.
Right, let's try that.
Say a little bit. Where systems work, what's the water source for those in the spring bed?
Oh, I'm not exactly sure if, I think they, for the clear water ecosystems, most of these ecosystems there, or these basins, the water comes from the, well, for the black and clear specifically from the Andes, like that's where a lot of that, catchment hydrology sources from. In the clear water, that area is more often influenced by groundwater dynamics. It doesn't have the same elevational gradient that exists.
Yeah, and the whitewater, do you just want to say what the whitewater is?
Yes, yeah, the whitewater is the way that it is because of a high proportion of sediment that comes from the Andes Shield, whereas the black water is so much darker because it has a much higher concentration of humic substances of decaying matter, and it doesn't receive the same level of inputs from the Andes Mountains. Yes,
Did you consider using some of the remote sensing data to kind of determine what was black water, white water, based on color? Is that possible? Or-
yeah, so the original map that developed those typologies, it's actually been around for over 500 years, like that has been used as a way of determining why how those systems are different. Then some very early ecosystem ecologists in the Amazon, Scioli and Junk, they were able to like help use a lot of previous historical records of determining what was black, white, and clear. And then more recent work has been done using remote sensing and satellite imagery to group some of those smaller tributaries that haven't been looked at to be able to see what geological material, like where do they exist in the geological landscape and what does their color reflect about how they fit into river chemistry.
But it's pretty relatively unchanging.
Yeah, good question. Yes.
I've got a question about the origin of these fires. Are these natural, these anthropogenic? Because this recovery concept seems like it could be very different if it's responding to a natural fire that might have had a natural way to recover versus a anthropogenic disturbance that maybe that system hasn't
That's a very good question.
adapted to. Or
And you'd expect maybe that if it was a more human source or intentional fire, that it would be less likely to be able to see the recovery to begin with, because maybe that system was intended to be converted to agriculture. In the Amazon as a whole, we see that many of those fires in recent years at least have been started by humans, but during the drought period specifically, it's more likely for spread over and spillover fires to go into protected areas when the conditions are just right. Those human level spread fires can go off into areas where it wasn't anticipated to spread. So yeah, it's a little bit of both.
but so there is a common feature to have lightning ignited fires in the Amazon, or are these all, or the majority of these maybe not intended for future agriculture, but this kind of escape fires?
Right, I would say the majority of unplanned fires are more escaped fires than the lightning strikes, although that can happen.
Any idea percentage wise? I was just, because it seems to me this recovery aspect, I mean, if you have a system that gets burned and it gets severely burned, and especially if you're starting to scarify the soil, and then you've got annual flooding that could be 50 feet deep, unless you've got a plant that can pop up really fast, it's gonna take a long time, it seems, because the system may not have adapted that sort of needed to adapt to that sort of response. So I'm just curious how much of this is anthropogenic versus, a natural cycle that you're monitoring.
Right, that's a good point, and most of the available data has found that it's not a natural cycle. In these tropical ecosystems, fire is very rare, and it generally wouldn't occur unless you had very specific climate circumstances, which generally haven't been there. It mostly does happen as a result of humans, which does, in the context of recovery, kind of does affect our interpretation of what we should be seeing. Yeah.
Just kind of going off of that, like,
Mhm.
the area in the northeast, is that just closer to humans? I'm not very.
So actually, humans are spread out throughout the region, and some of those areas have been, some areas have been burned intentionally for the spread of agriculture or human development. In the northeast, that actually is one of the drier areas. So there's where you'd see more of that interactive effect of humans live here, and the climate conditions can be just right at the time, during the dry season for those fires to escape. Mhm.
All right, I can't resist. So there's a lot of box and whisker plots, and they were tan and they were black, and so might have slipped by everyone, but. For the resilience, the time to recovery,
Mhm.
the time to recovery was. In the uplands
Uh-huh.
was, I can't remember, but then in the sluggishness one, the results were opposite. And
Yes.
so that's sort of like you were saying. They don't agree, the recovery time and the sluggishness. So if you go up one slide.
Mhm.
Then it was like, it's the time to recovery is longer in the black for the upland, so it should be,
Yes.
yes.
Mhm.
And then when you go down one slide, the AR1 is lower.
Right.
Does that match?
So this is, I'd say, so this one is telling us that things are taking, of the time series that we had that recovered, they took longer in the whitewater. So they recovered, they took, in the upland system, it took longer.
Yeah.
And then in the autocorrelation, we found that autocorrelation was higher here, so this was more sluggish. So that is a mixed response. I will be interested to see why that is.
Yeah, maybe pull some time series and let's look at it.
Mhm, yeah.
Okay. All right, any last questions from YouTube or Zoom? And. All right, that's it. Let's give another round of applause to soon to be. Good job. Excellent job. All right, thanks everyone. We will see you next week. Until then, take care.